Hi, this is the second part. This is part two of our class activity on calculation of the basic reproductive number using a computer algebra, symbolic algebra system. Okay, so this is the model that we are working with. Is the SIR model is a scenario in which state variables are denoting fractions or proportions and they add up to 1, and this parameter P is a parameter that denotes vaccination, right? And so we had used SageMath to do step 1 here of the computation of equilibrium points. So let's return to our calculations using SageMath. So we are in the process of reformulating the model now with the variables x and y. For this case, there is only one state variable in x and two state variables in y. So we have to use that command of declaration of this. These are the symbols. These are the variables in the sense of computer programming, right? And so whatever symbol or letter we're going to use, then we have to declare those using this var command. And we do this to redefine the three expressions. So now we're going to use h1, h2, and h3, and we're going to specify that each of those is a function. Each of those is a function of state variables x1, y1, y2, right? So it's rewriting the equations, and we can execute this cell of code. And by doing that with the command show h1, h2, and h3, then we get a display of the expressions. Now these expressions are in terms of x1, y1, and y2. And in terms of this new notation, then we solve again equations, the expressions equal to 0. We solve now in terms of x1, y1, y2, and we get these expressions, right? So as we had seen before, there are two solutions, two equilibrium points, right? And so the first equilibrium point is x1 equals 0, y1 equals this, y2 equals that. So this equilibrium point is the one that corresponds to the disease-free equilibrium, and the other one will correspond to the endemic. So with the disease-free, we're gonna define the operators that we call the gain operator and the loss operator. In this case, we're using matrices, using this command matrix, but this is kind of funny because this only has one, it's a scalar, it only has one entry, and we compute the partial derivatives. So here we're specifying that we want to take the partial derivative differentiation. The operator, the command is diff, and we say that we're differentiating with respect to variable x1, so we're differentiating the first entry of this with respect to x1. This is a little bit funny. The 0 here means the first entry. It's just due to the nature of the underlying programming language, high-level programming language is called Python. They have that type of thing. So once we execute the calculation of these partial derivatives, this is complaining here. See, I got an error message, so maybe I go back here, execute the definition of f gains and v gains, and now execute this command. So let me make sure we're in the same page. I'm putting the cursor here, highlighting. I execute this. We got that green pass there, and now I'm going to highlight. I'm going to highlight these two calculations, and then I'm going to execute that. And by doing so, then we get a display here of this is the answer. So the partial derivative of f gains of the first entry of x gains is the partial derivative with respect to x1 is beta times y1. The partial derivative of v loss with respect to x1 is gamma plus mu. And then I use that information to create matrices where these expressions are evaluated at the disease-free equilibrium. And with that information, the other thing to keep in mind here is this command V inverse, right? So we define the matrices and now multiply F times the inverse of V, and we get a display of such things. So in this case, what we obtain here as the expression is in this case, what we obtain here as expression is precisely what we are going to call the reproductive number. So these are, we'd have to compute the eigenvalue, the eigenvalues of this expression, but this expression is a one-by-one matrix. It's a scalar, right? So the expression equals, is exactly equal to the eigenvalue, but just to be sure, we have defined k, and then now we can use the command dot eigenvalues, and this is what we would get. So in summary, we have used the SIR model with vaccination, and we have done all these steps. We computed equilibrium points, we define the new notation with the non-disease state and the disease state and the non-disease state, and then define operators, define matrices, computed the next generation matrix, computed the eigenvalues, and then find out what is the basic reproductive number. That was all and good for this compartmental model with 3 compartments. Let's now repeat the steps for this model that has 1, 2, 3, 4, 5, 6, 7, 8 compartments. Okay, these are 8 compartments. V1 here denotes vaccination. V2 is also vaccination. S1 and S2 are susceptible states. This is basically the SIR model in 2 levels. There are 2 types of each of those compartments, and then there is an additional compartment here that is denoted with V. So with this model, we're going to call this model the SVIR model because of those are the names of compartments. And in this model, X1 and X2 are going to denote the 2 types of infected individuals. So the X compartments storing those with infection are going to be here X1 and X2, and everything else will be stored on the Y compartment. So Y1, Y2, Y3, Y4, Y5, and Y6, right? That's the other type of compartments. So what we're going to do here is to use this command var. Okay, now there are more symbols, there are more things. Notice that this includes the names of the state variables together with the names of parameters, small parameters, right? So this should look, there are so many things here that it would be tricky to look this in fitting in one, but there you have it, right? So it's one long line. So I'm gonna increase the size of font here, and then we're defining expressions. So now we're going to define H1, H2, H3, H4, 5, 6, and 7, right? So you have to go very carefully here. You can see the comments where each of these lines denotes, we're putting here in between comments the name of the state variables, the original name of state variables V1, S1, R1, V2, S2, and so on. And what we do next is to compute the disease-free equilibrium. We solve equations. So this command solves for, we're solving now 8 equations, and the intention is to find the equilibrium points and solving here for x1, x2, and so on, right? And then we can see that in this case, well, the expression, the solutions for these are quite involved, so you would get something really, really a long expression like this. If I reduce the size, you will be able to see it all fit inside the page here, and you can see these are very long expressions. Okay, very long expressions, very involved, but there are two of them. Okay, so what comes next is to compute the operators, the gain operator, the loss operator. Correct. So here would use the command matrix, even though this is a matrix with this is a 2 by 1 matrix. So f gains would be this first 2 by 1 matrix, and v loss would be this 2 by 1 matrix that appears here second. Okay, so what to do next is to compute partials, partial derivative with respect to x1 and with respect to x2 of the f operator, and then with respect to x1 and x2. So these are partials of the first entry of the f operator, and then partials of the second entry of the f gains operator, and similarly for the other operator. So here is what we obtain, and then we use those expressions to define a matrix called the Jacobian matrix, and we define f in this way and the matrix V, and in this case V is going to be a diagonal matrix. So when we multiply f times the inverse, we obtain this 2 by 2 matrix, and this would be the K matrix, is this 2 by 2 matrix. And then the next step that's non-trivial is to compute the eigenvalues of that 2 by 2, and it happens that these eigenvalues are equal to these two values. One of them is 0. Okay, so what we would consider the basic reproductive number is one of those eigenvalues, which is given by this expression.